Come on. All right. Because what I did last time was show how you get variation of parameters for a second order ODE. So all I'm going to do today is just jump from there to higher order. Okay, so, and where that method comes from. Okay. Okay. Now, so the ODE, and it would be linear, like usual. So it's going to be order P. So this is P's derivative instead of writing P primes, because I'm not setting P, giving P a value. And then you have some coefficients. So I'll call the coefficients A. And in the past, I've assumed, oh wait, I better be careful about this. You know what, I'm going to leave the coefficients constant. Plus A2y double prime plus A1y prime plus A0y is equal to G of t. Okay. Now, at least for time being, going to assume that the coefficients are constant. Although I should point out that variation of parameters, unlike undetermined coefficients, does not require that the problem be constant coefficient. It's just that if the coefficients are not constant, it's really, really hard, maybe impossible, to find your homogeneous solutions. Okay, so we have the same old initial conditions. So let's see, y0 is y naught, y prime of 0 is y naught. I'll put a superscript of 1. Y double prime is y naught 2, etc., all the way down to P minus first derivative. All right, so you have P initial conditions for a P order ODE. All right. And okay, so what you do is so I'm going to let y1 of t, y2 of t, up to yp of t by solutions of the homogeneous ODE. So the same ODE as this, except G of t is set to 0. So we have so for P4 ODE, we have P solutions, and they are assumed to be linearly independent. So we know it's known that such a set of solutions exists. Okay. All right. And then, okay. All right. now define this matrix. Fancy X of t will just be a P by P matrix consisting of first row will just be those solutions. Second row will be their first derivatives. And all the way down to the P minus first derivatives in the last row. Okay. So because the solutions y1, y2, etc., are linearly dependent, that x of t is invertible. So now I can use the same formula to write down the solution to the original initial value problem that I did in the second order case, just everything appropriately generalized for higher order. So what happens is we get y of t is first component of x of t, x of 0 inverse times the vector of initial values. I'll just call the vector y naught. Okay. Okay. And that is the matrix exponential. Well, x of t times x of inverse, if you recall from a couple classes ago, that's one of the ways of writing the matrix exponential, where this is, if I were to rewrite this higher order ODE as a first order system, u prime equals AU, where u, the vector, consists of y, y prime, y double prime, all the way down to the p minus first derivative. Okay, so if we wrote the system this way, this would give us a solution. And the first component of that solution is just going to be y of t that we're after. Okay. And then for the source term, we have x of t integral from 0 to t, x of s inverse times the vector consisting of all zeros. And the last component is g of t, the right-hand side, or g of s, the right-hand side of the original problem. Okay, so this is the same solution formula we've been working with, it's just for a p-folder problem. And I've done a lot of notation on you. Are there any questions up to this point? So this last term here, what it says is that the solution includes, so this whole part is called the particular solution. And the way it's written indicates that, that the particular solution is a linear combination of the solutions of a homogeneous problem, except that the coefficients in linear combination are not coefficients, they're not constants. They're functions of t that come from this. Because once you evaluate this is a vector function, and then you have a matrix vector product. Now, in the second order case, when we had to deal with this, we just used a formula for the inverse of a 2 by 2 matrix. But now we have a P by P matrix. And to solve, so now we have to solve this system. But we don't want to do like, Gaussian elimination or we don't want to deal with numerical methods here. We're after a solution formula.
Oh.
Yeah. So what is a way that's taught in linear algebra classes to get a formula for this? The solution of a system of equations.
Okay, what is the way to get a formula?
Yeah, there actually is something that's taught in linear algebra classes. Well, I guess it depends on the instructor, but it is a way to express get a formula, a nasty formula, but still a formula for a solution of AX equals B problem. I'll give you a hint. It involves determinants.
It involves.
Well, yeah, it's probably been quite a while since you've seen it.
I don't know.
Kramer's rule.
Kramer's rule, okay.
Yeah. So.
Oh, I forgot about Kramer's rule.
Oh, that's a good thing I'm touching on that.
Huh?
This is a good thing I'm touching on that.
Yeah.
So to solve a system, x of s times, I'll call this w of s, is equal to this right-hand side, 0, 0, 0, g of s. Because really that's what we're doing. We're solving this system for the unknown vector w of s. We'll use Kramer's rule, which I will review in a second. Okay, because once we have that, then we're done. We can just so that will give the integrals would have to be worked out and all that, but that would be it. Okay. Are any questions up to this point?
I just have to apologize to Mr. Kramer for forgetting everything about him.
Okay.
I literally don't remember anything about it.
Okay. All right. Oh, how much time do I have? Not much. Okay, that's fine. In fact, really, there isn't anything left to cover except Kramer's rule. So I'll just talk about it from perspective to solving any old system, AX equals B. And there's just be applied to this where everything's a function. Okay, so all right, so Kramer's rule for AX equals B gives a formula for each component of a solution, X. And it's a surprisingly simple formula, at least in appearance. The determinants of matrix I'll call AJ divided by the determinant of A, where AJ is a matrix obtained by replacing the jth column of A with B. Okay. So for each component of x, like so for x1, you replace the first column with b, get the determinant of all that. Then x2, you replace the second column of a with b, determinant of all that, and so on. So there's a total of n+1 determinants to compute. Now, determinants are really expensive. For n by n matrix, in a general case, the best way to compute a determinant still involves over n cubed operations. If you're doing everything by formulas, like how in your first linear algebra class you would spend time like doing a determinant of a nasty 4x4 matrix, and then have these cofactor expansions and all that crap. Mm-hmm. Yeah, so when you do it that way, the number of operations to compute a determinant is n factorial. So it's horribly expensive, but in a class, you're only doing it on tiny matrices, so it's still tedious as hell, but you don't realize how awful it would get if you did it on something larger. So to write down a formula for a solution of x, like if all of these entries were symbolic, for instance, it would take the order of n factorial operations to work all that out. So this is a terrible method compared to 610 type methods in terms of efficiency. But when you have a small system and you really do need a formula, because if the entries of A and B are not numbers, then what choice do you have, really? Okay. So you do these determinants, and in the case of our ODE setting, the denominator, determinant of A, that happens to be the Wronskian. The Wronskian is the determinant of that matrix fancy x of t. So variation of parameters always has a Wronskian in the denominator for each of those integrals. All right. So the only thing I want to do, and I don't have much time left anyway, is to give you an idea as to why Cramer's rule is true, using properties of determinants. Okay. So, all right. So what you do is, so I'll put proof, but in quotes. It's not rigorous, but it gives you the idea, and certainly could be made into a formal proof. So what you do is, first, you multiply column J of A by Xj. And what happens is, whenever you multiply a column of a matrix by a number, that multiplies the determinants by that number. So scaling a row or a column scales the determinant. Okay. Then what you do is you add x1 a1 plus x2 a2, etc. xj minus 1 aj minus 1 plus xj plus 1 aj plus 1, and so on up to anx or xn an. Whoops. An. All right. To column J, same column. And if you notice how I wrote this, J is skipped. So you're taking all the other columns of A and multiplying them by the corresponding components of X. And you take all of those scaled columns, add them to column J. Well, what does that do to the determinant? Nothing. The determinant is not changed when you take a multiple of one row or column and add it to another row or column. But then take a look at what column J is. Column J is equal to a sum, k equals 1 to n, of column K times xj, xk. So this is a linear combination of the columns of A, all the columns, times the corresponding components of X. Well, that is the same as AX, which is B. So what you've done is you've just transformed A into a matrix where the jth column is now B. So you've just formed the matrix AJ. But the thing is, when you transformed A into AJ, the only thing that happened to the determinant is it got multiplied by xj. So the determinant of AJ is equal to xj times the determinant of A. And so you just rearrange and you get the formula. And that's it. That's the proof of Cramer's rule. Questions about that? The only thing I find kind of unsatisfying about this proof is really one of the properties of determinants that's used. It just seems counterintuitive that if I scale a column by a number, it scales the determinant. But then I do all of this, I add all this crap to a column, and it doesn't change the determinant at all. And that just seems kind of implausible. So I actually took a little time to try to convince myself that that really is true. And I actually did, because I wanted to go back to the definition of a determinant. The definition of a determinant is if you take all possible permutations of 1 to n, and you pick you go down the rows of A, and you pick an element from each row according to a permutation, and then you multiply them all together, and then you multiply that by the sign of a permutation, plus or minus 1, and you add them all up. That's the determinant. Then what happens if I replace one column by all this, or really just a multiple of another column to it? And what you find is that you end up with, for each entry in that column, like there's two permutations that apply. One is a transposition of the other, so they have opposite signs. And the terms that are added because of this end up canceling out. So, I know it's one of those things you have to see, and I don't have time to really get into it, but yeah, that's why it works. Because of how permutations work. So go figure. All right, so yeah, so this leads to a method that's taught in ODE classes for carrying out variation of parameters for higher order ODEs that they have to get their homogeneous solutions, put them in a matrix, and then use Cramer's rule to work out the x of s inverse times that vector, which in this case is all zeros except for the g at the bottom. They compute those determinants, so it's a really nasty problem to give on a test. And then they can write out the solution from there, similar to the second order case. But for a p order equation, you have p integrals to work out. So, okay. So, well, I'm out of time for today, and then so we won't meet Thursday. The next thing I would do is undetermined coefficients, which I don't have to wait till after a break, honestly. So, no. Okay, let's not meet Tuesday either.
Huh?
Let's not meet Tuesday either, because then I'd be starting a topic, and then I wouldn't see you for a week, and there's a wedding happening in the meantime, and and
So
then
we won't meet until after fall break for topics. For this
Right.
class.
Well, I see what you're saying. I was wondering.
Yeah,
like,
so-
fall break. Yeah.
so 2 weeks from today, so the 26th will be our next meeting here.
Okay.
All right. Yeah, you wouldn't find me on that. Okay, I'll stop the recording.